proportional to the long-term value. So an idea would be to put the candy in a jar that gives mild shock. So whenever you try to eat the candy, you get a big shock. I mean, a shock and say, heck with it, I won't eat it. And you are only optimizing your local reward, but unbeknownst to you, you are also optimizing your global cumulative reward. So this is what is called reward shaping. This is what is called making, changing the society such that most of the people who are bozos and just go for the immediate reward will still do the right thing for themselves. Do you understand what I'm saying? And it turns out actually it's an extremely important idea, because rewards are not just God-given in any sense. You can incentivize an agent to do the right thing by changing the reward structure. But all of this comes from the fact that values are very different from rewards. In fact, values don't have to be proportional to the rewards at all. If I tell you that value of S2 is less than value of S1 for a given policy, you don't know anything about the reward of S2 and S1. For that, you need to know the rest of the world, which basically means you need to know the entire, reward structure in the rest of the world. You see what I'm saying? Okay. Okay, so you figured this out, and so now for finite horizon, basically the value function is we first consider maximizing the total reward over the finite horizon, which is what we are trying to do. And then of course, for the finite horizon, we do know that just like the policy, value is also dependent on the actual stages to go. So in fact, this should have been written as K for all K. Because for finite horizon, it's not just one value per state, it is one value per state for the amount of horizon left, the number of stages left to go. You see what I'm saying? Okay, so it turns out that basically we have this function called the value function, which for finite horizon will be written as V pi k. Pi is the policy, candidate policy. K is the number of steps left to go. And if the horizon is 100, then k can range from 0, 1, 2, etc. all the way to 100 steps left. And for each of them, I get a value for status. Okay. So now the interesting thing is this is the formal way of writing what I was saying in the last several minutes. So I'm saying the k stage left to go value of status with respect to policy pi is essentially the expectation over the cumulative reward you will get using pi starting from S and going the total number of horizon, number of steps. And then this E, expectation, is what essentially is the right way of sampling the policy. I just put expectation and say you know what to do. But I was telling you earlier, just add them up and divide by the number of times you should get the policy. That's an empirical expectation. This is a theoretical expectation. Okay? So now in particular, essentially what this can be unpacked to is you are actually, these rewards that you are getting depend on the states. And that states you go to depending on the actions you do. And the actions are what are given by the policy. Okay? This is basically the way the value of the policy is defined. Okay? Now, so it turns out that I can actually compute this, which I was telling you the only way to compute it is by this crazy simulation method, sampling method. It turns out you don't need to sample. You don't want to forget that you can sample. It turns out sometimes much later than this course, you might very well say the best way to figure out, approximately the value of a state is sampling. But in this class, you want to realize that actually, for finite horizon MDP, there is a way of writing a set of, essentially, set of equations that will just give you the value of the policy. How do I do this? Start from the fact that if I'm talking about v pi k, remember when I'm trying to compute v pi k for all values of k. So the first thing I'll do is I'll compute v pi 0 of a state S. V pi 0 of a state S. What is that? If I have 0 steps left to go, I'm in state S, what is the reward I get? What is the total reward I get? The total reward I get is the reward I get right now. That's it. Because I'm no longer going to live after this. So beautifully, V0 pi S is R of S. This is given. So I got one part of the value function already. Then I need to know essentially, if I know the values, let's say this is V0 of this state and V0 of this state. Suppose I'm trying to compute V1 of this state. Okay? Turns out, let's say that the policy is telling you that I should do in this state an action A, which with 0.7 takes me to this state, to 0.3 takes me to this state. So then I can say that the reward, that the value of this state with one step to go is of course the reward of this state plus 0.7 times the 0 steps to go reward of this state and 0.3 times the reward of 0 steps to go of this state. Do people see this? So if you figure out what to do for 0 steps to go, then you can just back propagate and figure out what to do with 1 step to go. And what's the value with 1 step to go for this policy? And if I figure out 1 step to go, then I can figure out 2 steps to go. If I figure out 2 steps to go, I figure out 3 steps to go. So in general, if I have figured out Vk minus 1 pi of states, then I can compute Vk pi of a state S as R of S plus what I did here, which is I take, given the state S, what does my policy say I'm supposed to do in state S, given that I only have k steps to live? Remember, I'm assuming that the policy is wrong. Oh my God, not good. Not good at all. So I might be in trouble, but we'll see how far we can go.
Do you need a charger?
Do you have a surface charger?
Yeah, I do.
Okay, that'll be good. Thank you. Yeah.
This is what you watched on the video.
Yes. I'm just trying to explain to you why. Okay, it's not like it's going to No, it's not broken. Okay, let me just change it.
It's not Gen 3 or above?
No, that's fine. I can use the other one. Okay? I can't write down this, but otherwise we can continue talking about this. Okay, so all I just said is there is this nice recurrence relation, dk pi is connected to dk minus 1 pi. Okay, and what that basically means is you compute V0 with respect to pi, and if you compute V1 with respect to pi, then you can compute V2 with respect to pi, V3 with respect to pi, all the way to Vk with respect to pi, and you're done. That will just give you the value of a single policy. Now you might ask, how do I get optimal policy given this? Well, if I know how to compute the value of a single policy, I can just compute in a dumb way at any rate the value of the optimal policy in the following way, which is, remember we know how to compute two policies. Given two policies, you can essentially compute, you can see one is better than the other by comparing their value functions. Okay, and it turns out that there are really only a finite number of policies. There are just a power t times s policies, that's all. That's not a big number. So you put a big loop and then guess a policy, find its value function, and see if it is the best that you have seen till now. Except remember, this is a huge vector value function. Right? Okay? So you are essentially finding the max value over all the policies. And the one which has the best value, you give it out and say this is the optimal value function. Is that obvious? You should understand the dumb way of doing things before you understand the better way, so that you will really feel good about it. Okay? So now the problem is that this brute force approach has exponential complexity in the number of states. And the problem, part of the reason is, in some sense, you are computing each policy as if, from scratch, the value of each policy from scratch. And so you're repeating a whole bunch of computation, Now, what you can do is, to heck with computing and comparing policies, let me just directly compute the optimal value function. And if I compute the optimal value function, then I can always compute the optimal policy function. Okay? The interesting thing, of course, is, let's look at this picture. I'll go to the formal theory to make it. Imagine this state S that we were looking at previously. With a pi, imagine it only has two actions, A1 and A2, that are possible in this state. In the previous case, we were looking at this orange part, where we said the particular policy I am considering, pi, was asking me to do A1 in state S. Right? Okay? So, and then I decided that if I were to do A1, what is the cumulative value I will get for S? But notice that while there are a huge number of policies, their projection at this particular point, there are many policies, and policies can be different from each other just because they do a different action for one S and one K, that's it. So you can have two policies which are exactly the same everywhere, except for a particular state with a particular horizon. They give different actions. The moment they do it, they are two completely different policies. Right? So even though there are many different policies, if you look at the projection of those policies as to what is supposed to be done in S, the policy will either say take A1 or A2 because they only do those actions possible. Right? There are only a number of actions that you can do, so either you will do that or that. Now, if you were to do that action A1, I would be getting this much by backpropagation. And I would have just added it to RS and I would have been done as far as policy computation is concerned, value of a policy was concerned. But right now I'm not talking about a single policy, I'm talking about all policies. And I'm talking about what would the best policy do in this case. What would the best policy do in this case? Now, one policy could have, a set of policies which do A1 here would have given me this. The other set of policies which would have done A2 here would have given me that. What do you think the best policy will do?
Pick the maximum.
It's not obvious. It will do the best of these two. Take the max of both. Right? So if I do max of this and this, add up the RS, then I will get directly the value for t plus 1. Notice there is no subscript pi. You see that there is no subscript pi? That basically means this is the granddaddy of all the value functions. It's the best value function. Now that you've figured out the value function, you just need to figure out the policy. Now, do you not know what the policy is? Actually, you could have kept some bookkeeping. Remember, this is sort of the way A star did too. It will pick in every path that is expanding, it will pick the child that has the best F value. And then after you reach the minimal path to goal, you essentially remember the pointers and reach the top state. Right? That's what you do. So in fact, what you do here is when I did this, whichever was the max, whichever was the action that actually led to the max, I remember that as the action to do. Did you guys see what I just said? Now, for finite horizon case, this is all you need to do. In fact, you compute the optimal value, and as a converter, you actually compute the optimal policy too. And check it out. With all this humongous build-up, it looks like a total letdown. Extremely easy stuff to do. Okay? So, now I go back to this and I show this is of course the formal way you write this. And you should be able to see this and see this there, essentially. Okay? All I'm saying is, we are no longer talking about values for policies. We are talking about value, optimal value function. Okay? And the optimal value for V0 of S, nicely enough, doesn't depend on the policy. Because V0 of S is still known as just the reward of S. Because it doesn't really matter what the policy says, you're dead. This is the only thing, this is the only state that you will ever be in. And so you'll get the reward of S. And then I told you that if you know Vk minus 1 of S, all the states, Vk minus 1 of all the states, then you can compute Vk of all the states by doing a computation which looks extremely similar to what you did before, which is taking the summation, except you are now taking a max over all the actions. Previously, there was no max. If you look at if you just look at the way you computed the value of a single policy, there is no max. Because the policy tells you what action to do. When you are computing the optimal policy, there is no single policy you have. You are actually comparing different policies that will differ here in terms of the action. Okay? And so, essentially, you consider all possible actions you can do and then see which one is giving the best value of this sum. And you take that, add it to RS, that will be the value. Okay? And then, of course, once I compute the optimum value function, optimum policy is just bookkeeping. Because pi star sk is the action that was actually giving the optimal sum of those. Okay? So the action that did Argmax over all the actions, the one basically, so basically, if I just have this, the value, I already know the values of all the states, then the optimal action to do, optimal value for all the states with respect to horizon, then the optimal action to do here depends only on which of these branches lead to the bigger number. Okay? So this is why you saw that example that you did in the class 2 classes back, I asked you to see, which is essentially the way you compute the finite horizon value iteration is, this is called the value iteration. You're iteratively computing value for horizon, number of stages left to be 0, 1, 2, all the way to 2. So you start by initializing V0 to just the RS. And then if I know V0, then I can compute V1. Okay? Because the way I will compute V1 is, let's say for this particular state, there are 2 actions. Let's say you would see which action will give me better backup value. Okay? Better backup value. And then, so similarly, I do it for all the states. And if I compute V1, then of course, I take the better backup value, add up that particular state's reward, that will be the value of that state with 1 step to go. Now I can compute value of the state, each of the states with 2 steps to go in terms of the value of states with 1 step to go. And I keep doing this until I reach the horizon that I have. Okay? That's the way you compute the optimal value function. And in doing so, you also compute the optimal policy. Okay? So I'll leave this here and let me actually do this attendance thing because we're supposed to do that. Okay, let's just write okay. Assuming you need it, okay? I'm just going to say, you say yes or no and write whatever you want, and this is your attendance, okay? Start. Okay, 91 people, 98 people. Let's do it fast. Go back. Okay, I'm stopping. I am stopping. Okay. So, I forgot to tell you that your names will be on this board, so I will pass this to PAs. So when you go next time, you said no or some smart aleck thing, don't be surprised if they ask you to stand way back in the line. That's okay. But it's actually a serious question. We are trying to see whether you need more time. So this guy who's leading right now, we should remove his attendance.
I have a meeting.
It doesn't matter, I'm sorry. Okay. I waited for enough people to leave to take that. Okay, so value iteration we are talking about, by the way, notice how you use what's called the optimal substructure property of the value function. Optimal substructure property of the value function. If you have the same MDP and you think you'll only have 1 year to live, and you computed the optimal power, and doctor came and said, hey, we found that you actually have 2 years to live. You don't say, oh my God, I have to now spend an entire time recomputing the policy. No, you already know what are you supposed to do if you only have 1 year to live. You just extend it when you have 2 years to live. Do you see what I'm saying? So it's like the amount of work that you have to do is going to just be lower because you're taking the optimal policy with k steps to go to compute the optimal policy with k plus 1 steps to go. This is the optimal substructure. And whenever this happens, you know, you have these ideas, basically dynamic programming algorithms. Yes?
Is this caused by the fact that you use the expectation program?
No, it actually is caused by the fact that you are using Markov property. You care only about the state. The value of a state depends on the state itself, not on how you got to the state. See, how you get to the state is this direction. Right? Because this is the beginning. The value of a state has nothing to do with how you got there. It is what you get from there to the end. That's the Markovian property of the state. That's what you wind up using. Okay? So that's one thing. The other thing is, because of the finite horizon, the policy is non-stationary. That's why we computed V0, V1, V2, V3, etc. Okay? And what's the computation time? There are 3 iterations. At each iteration, there are each states S. You have to compute the expectation of the actions. So essentially, the expectation can be done in n time, O n time. So the total time complexity is order of the horizon, the number of actions, and the square of the states. Square of the number of actions. And you might remember that square is a polynomial. And you also might remember that polynomial is good. Okay, so this is essentially the cost of computing the optimal policy is only polynomial compared to the dumb idea I came up with before, which involved just computing enumerating all the policies and seeing which is the best. So you went from exponential to polynomial by using the structure. Okay. The other things is the following. For the finite horizon, if you compute the optimal policy, then you can compute optimal value, you can compute the optimal policy from that, and that will be the optimal policy. That means there can't be any other policy which is better strictly than this. There may be other policies which are just as good as this policy, but not better. That's what we care about. And in particular, that's where this point comes in. Given a finite horizon MDP, there is a unique optimal value function. But there may be many optimal policies. There is no single optimal policy. Could be, but there are many policies, all of which would give the same value. Okay? So that's something to keep in mind. Optimal value function is unique, optimal policy is not. This actually winds up being important even when we get to infinite horizon cases. And because many policies can have the same value. So now we'll talk about infinite horizon. And then we'll talk about next class. So in the case of infinite horizon MDP, the good news, it's good news and bad news situation. The good news for infinite horizon MDP is that in essence, it's like the policy has to be stationary. Because if the policy were to be non-stationary, it is like I've already lived 20 years of my life. What am I supposed to do in this state? Versus I've already lived 35 years of my life. What am I supposed to do in this state? Now in both cases, if it's infinite horizon, you still have infinite amount of time to live. Do you see what I'm saying? So there cannot be any non-stationary policy for infinite horizon MDPs. They just cannot be. So you only have stationary policy. So on one hand, it looks as if you thought of infinite horizon, remember the number of policies for finite horizon was a power t times s, whereas is the number of states. T is the horizon. If you think like the most obvious way, when you get to infinite horizon, it's a power infinity times s. So there should be infinite number of policies, infinite number of policies. But there are no non-stationary policies, there are only stationary policies. So instead of infinite number of policies, instead of going from a power t times s, you go where t equal to infinity, just go to a power s. That's it. Big win. If you live infinitely long, then you only need to think of one policy, not a non-stationary policy. Okay, that's very, very nice. Yes?
Does that mean you can find your optimal policy faster?
That's what we're trying to do. That's what we're trying to do. Okay, now, so given this, I would actually say that there is in fact a way of computing the value function. It's only one value function, right? It'll look exactly like this. It looks exactly like this. In fact, so now just look at this and think infinite horizon MDP. Okay, you have infinite horizon MDP has only a single value function, and it's a single optimal value function. I'm trying to compute this optimal value function. And what I will do is I'll start by acting as if I'll initialize the value function, V0 to some value. Okay? Act as if you just initialize the V0 to be R of S. In fact, it's not needed. It just initializes to something else. In the case of finite horizon, V0 has to be initialized to the actual reward function. For infinite horizon, V0 can be initialized to anything. But act as if you initialize to RS. Then I can compute V1, sorry. Then I can compute V1 like just before. And then I can compute V2, V3, V4, etc. Except this is not horizon, this is the internal iteration of your program. Now think logically, if there were to be an optimal value function, as you keep doing these iterations, maybe between two iterations the value function won't change at all. And then you'll say, I have reached the optimal value function. I mean, the theory still has to be actually explained, but this is the intuition. So in some sense, what you do in infinite horizon case is exactly what you do in finite horizon case, except in the case of finite horizon, these iterations have physical significance. This is what you would do if you have one step to live. This is what you would do when you have two steps to live and so on. In the case of infinite horizon MDPs, when you do the same exact value iteration, the V1, V2, V3, all Vi, they are just intermediate results of your computation. Intermediate results of your computation. They actually have no physical significance. But if in fact there is only single optimal value function, then doing this, hopefully, will get you to what's called a fixed point. That means irrespective of where you started from, you will actually reach the optimal value function after some number of iterations of this. It turns out that you cannot actually put any limit on the number of iterations required, but it typically turns out that after a few iterations, the value function from